Welcome, everyone. Pleased to have you here with us for today. I think it's our 45th or 46th episode of This Is CDR. This Is CDR is an online event series presented by OpenAir to explore the range of carbon dioxide removal solutions currently being researched, developed, and deployed, and to contextualize them for policy proposals OpenAir is working to advance in New York State, other US states, and localities and jurisdictions worldwide. Everyone, if you haven't done so, and I see many of you have, please introduce yourselves in the chat and tell us where you're zooming in from. My name's Toby Bryce. I'm based in Brooklyn, New York, and I work on CDR, policy advocacy and market development with OpenAir. Just some quick background on OpenAir. We are sorry, the slide's not changing. We are a distributed volunteer network dedicated to the advancement of CDR solutions that are essential to solving the climate crisis. And global community where we work together on shared open source missions in the areas of policy advocacy, research development, and activist CDR market and business development. There should be some links in the chat to join our group. You can fill out a form and we communicate and organize our projects on Discord, which is similar to Slack, and we'd love to have you there. There's plenty of things to work on, and it's also, I will say, a lot of fun. Before we get started with the program, one thing we always like to do is define what we're talking about when we say carbon removal. And here it is. This is a definition from the CDR primer, which is a great resource, and we'll put a link to that in the chat. It's also essentially the same definition that's used in the IPCC reports. Carbon removal is human activity, purposeful human activity to remove CO2 from the atmosphere and to durably store it in geological, terrestrial, or ocean reservoirs and in long-lived products. There are two really important things to call out when we talk about CDR. Number one is that CDR is commonly confused with carbon capture in the media and elsewhere. And carbon capture typically means capturing carbon dioxide from a point source emission like a cement plant or a natural gas plant. This may or may not be a good climate solution depending on the situation, but it's a form of emissions reduction and it is not carbon removal. Again, carbon removal is a purposeful human activity to remove CO2 from the atmosphere and to durably store it and durably put it away in the earth or in the ocean or in long-lived products. Number two, it's really important when we're talking about CDR to emphasize that carbon removal is in no way, shape, or form a substitute for reducing emissions. We need to reduce emissions and decarbonize the global economy as quickly and as completely as possible, full stop. That said, there are going to be certain emissions that are difficult or inequitable to abate, and for those, we are going to need carbon removal. And there's pretty clear scientific consensus that we're going to need carbon removal at immense scale, gigaton scale, that's billions of tons per year by mid-century. Again, to abate these, for the hard to abate emissions. And we are currently at kiloton scale. So it's really important that we start working on CDR right now because we need to scale it up to many orders of magnitude more than where we are now by mid-century. We can't lose sight of the priority on emissions reduction. So these are both essential climate activities along with adapting to our current already altered climate. And none of them substitute one for the other. So we need to be working on all of these things. And we're here to talk about CDR. We're going to put some resources in the chat if you want to learn more. We've run 40 plus episodes of This Is CDR, so this is a great place as well to learn about the different ways that you can remove carbon removal from the atmosphere. And today we're very excited to have a very innovative direct air capture company from the Netherlands with us. And Mega Raghavan, my colleague, is going to hop on now to talk about the run of show and then introduce today's session.
Hey everyone, I'm Mega. I am an OpenAir member based in London, and I work on policy advocacy opportunities, mostly in the US where I'm from. So as usual, we'll have a format of having a short presentation first, followed by a few prepared questions, and then we'll have moderated audience Q&A. So please type any questions you have into the Zoom Q&A box as we go along. Make sure you find the one that says Q&A because that helps us to organize it separately from what's going on in the chat. The event is being recorded, so we'll send the video link to everyone who's registered, and we'll also post it to OpenAir's website and to our YouTube channel. This week on This Is CDR, we're very pleased to welcome Carbyon founder and CEO Hans de Neve to present the company's novel, Prize Milestone Award-winning fast swing DAC process, which employs a continuously rotating drum that consists of activated carbon fibers functionalized with amines. Hans founded Carbyon in 2019 as a spin-off company from the Dutch research institute TNO. At TNO, he was working on novel materials and production technologies for solar panels. He's trained as an electronic engineer and material scientist. His PhD is on 3 to 5 semiconductor materials. And he worked for many years at Alcatel-Lucent before engaging in the domain of renewable energy about 10 years ago. So Hans, whenever you're ready, feel free to jump on and get started.
Okay, many thanks, Mega, for this introduction. So this is about Carbyon, and it's an adventure that started, let's say, Carbyon was founded 3 years ago, but my adventure personally started more than 10 years ago. I was attending a Christmas lecture given by a professor talking about solar fuels. And in those days, I was still working on smart grid technologies, and I knew everything about matching production of electricity with demand of electricity, and specifically given the intermittency of wind and solar, this was quite a challenge. And when I heard this person talking about solar fuels and the ability to transform electricity, also renewable electricity, obviously, into hydrocarbons, this was an eye-opener for me, because I realized that indeed, if we could effectively store renewable electricity in the shape of hydrocarbons, that could actually enable a lot of the hard-to-abate sectors to actually use renewable electricity. But in order to make hydrocarbons, you needed two components. That was renewable hydrogen, but also a renewable source of carbon, which turns out to be CO2 or carbon in the form of CO2 coming from air. Now, in those days, 10 years ago, this was still a far-fetched dream to capture CO2 from air, or at least to do it in a cost-effective way. I remember in those days there were companies like Climeworks and Global Thermostat and Carbon Engineering that started off in what was then believed to be an impossible task. Nobody believed that it could be done in any cost-effective way. Thermodynamics would actually turn that too difficult. I think today, 10 years later, we see that there are a lot of proof points that it is effectively possible to capture CO2 from air in a cost-effective way. We're not yet there, and this goes for Carbyon, but this also goes for many other companies. So the industry, I would say, is not yet there that we can actually do it at large scale and in a cost-effective way. But I would say there is good hopes today using the latest technology and the latest insights that this would effectively be possible. Now, let me talk to you about Carbyon, which is, as mentioned and in the introduction very nicely described, it's not about capturing CO2 from flue gases. It's effectively capturing CO2 from ambient air. Of course, we as humans have emitted way too much CO2 into the atmosphere. And so even if you stop tomorrow emitting CO2, climate change will continue for a very long time, unless we can also undo, let's say, the abundant CO2 that we added to the atmosphere. And that's where direct air capture comes into the picture. It's not replacing existing efforts, so we should, of course, try to reduce our emissions. We should do reforestation, we should do point source capturing, we should do all of those things. I think for anyone who has worked long enough in the area of energy transition, we know it's an and story. It's not one solution or the other. We will need all of these solutions, but we will also need direct air capture. It has been recognized recently by the IPCC and by some other entities, and that's rather new, because like 5 or even 10 years ago, there was no way that anybody took it serious, that direct air capture might play any role in the energy transition. I think today, many people think it will, many people hope it will, because it does enable a great number of things. But the big challenge, of course, is the cost. If you look at existing technology, we still talk about 500 euro per ton of CO2, at least, and that has to do with the large energy consumption, so the high OPEX, but also has to do with the high CAPEX costs per ton of CO2. And the capex cost is mainly because existing processes are rather slow. And with that, I mean that it typically takes several hours for a sorbent to be saturated with CO2. And that means you can reuse that sorbent not very often. And if you want to reach a certain yield, that leads to very bulky type of machines. You need a huge machine to get a certain yield of CO2 per year. And that's where we try to look for a solution. What Carbyon did, and we tried to improve the kinetics of the process. So to make things faster. That's also why we talk about a fast swing process. Whereas in some other cases, you have a swing cycle of a few hours. We aim for a swing cycle of a few minutes at most. In terms of design of the machine, I just give you a preview about how things will or might look like in the future. We have defined a single unit which will be roughly filtering 100 ton of CO2 per year as a kind of cylinder, a vertical cylinder, which takes in ambient air at the top, ambient air which is then exposed to a filter inside, and I'll talk about that more in a minute. These are independent units, they can be put in an array, so to build bigger farms, of course, up to 1 million or more tons per year. But so each individual unit operates on its own, will roughly filter 100 ton of CO2 per year from the atmosphere. And in terms of size, you need to think about this cylinder to be roughly 2 meters in diameter and 4 to 5 meters in altitude, in height. Now, I talked a little bit about existing technology and about, let's say, the adventures that started more than 10 years ago, like Climeworks, Global Thermostat, and also carbon engineering. So how does this technology from Carbyon compares to what, let's say, these companies have done? In a way, I would say we probably resemble most what Climeworks and Global Thermostat have been doing. So just like them, we work with a solid state sorbent, which I'll explain more about in a minute. It's based on amine technology. In this case, amines functionalized on activated carbon. So it resembles very much the solid state or the solid state sorbent technology that also Climeworks and Global Thermostat have been looking into. But the difference is the kinetics. So we have improved the speed, and I will explain in a minute how we came to improve the speed. Compared to carbon engineering, as many of you might know, they use potassium hydroxide, which is a liquid solution. So we that led to from a machine cost point of view, an interesting solution, but from an energy point of view, liquid solutions will probably always take too much energy to work in a proper way. So we followed the route of Climeworks and Global Thermostat into a solid sorbent, but we did it slightly different. One difference is that it comes as a rotating drum. And so what we have, actually, we have a carrier, which is the wall of the drum. So what you see here is a cross section of the cylinder that I've shown you a minute ago. So as you can see, it consists of 2 chambers. Well, I'll show my pointer, that maybe is a bit more obvious to the audience. So it consists of 2 chambers. You have a left chamber here, which is the air chamber, and you have the right chamber, which is the CO2 chamber or the regeneration chamber. It's not like on the picture here that air comes from the left and CO2 left on the right. Actually, air is blown from the top of the cylinder, and CO2 leaves actually at the bottom. But anyway, for the sake of this discussion, this is not so important. What matters is that within the cylinder, there is this rotating drum, which is rotating in a continuous way. And the wall of the drum consists of a high surface area material, The material actually is a set of woven activated carbon fibers that have been functionalized with an atomic monolayer of amines. And I come in a minute back to the reason for doing it in this specific way, meaning the atomic monolayer. But for the sake of the principle, it's like of a pump. So in this section of the machine, the material is exposed to air and will saturate with CO2. After, let's say, a minute, the drum finds itself in the other section of the machine, where it will be heated to 100 to 120 degrees Celsius, which will release the CO2 from the material, and the CO2 is then pumped out of this section of the machine. So it's a continuous process. This drum is rotating in a continuous way. That also means that, of course, there are slit openings on the top here and on the bottom here to allow the drum to pass through. And it's so continuously pumping, let's say, CO2 from this region, captured from air, to this region where it is released again. The details about the material, it's shown here. So it consists of a woven set of fibers. The fibers themselves are like 5 micron in diameter, and the fibers are porous. So these are porous activated carbon fibers. These are commercially made fibers, so we don't make them ourselves. We purchase them. You can buy them in woven structures like over here. You can buy them in felt structures, so all the fibers individually, randomly structured. The material looks like a black felt, let's say, but the nice thing, of course, is that this material has roughly between 1,000 and 3,000 square meters of surface area per gram of material. So it's a huge internal surface area. And what we do with this material, so we functionalize this material with atomic layer deposition. This is a technology that was developed for microelectronics purposes, but also for solar panel purposes. It's the ability to modify the surface of a material with one atomic layer in a kind of with self-limiting chemistry, so that it's uniformly coated with a single atom layer. And so in this case, what we do, so the internal surface of these fibers, which you can't see visually, of course, here, the dimensions are too small, but we functionalize them with new materials. And it's actually better shown on the next slide. And so when you have a single pore, let's say, inside of one of those fibers, at the pore opening here, it's quite small. It's only a few nanometer. Actually, on the top side here, you see the pore size distribution, which is the size of the pore openings that you have in this material. So it's not just a single value, it's a kind of distribution, but you see that the pore openings are between 0.5 nanometer and up to 1.5 nanometer at most. So we talk about really small openings and small dimensions. And what we do, so in that, let's say, pore, which has an opening of a few nanometer and a depth of, say, roughly 1,000 to 2,000 nanometer. And remember, the fibers are 5 micron in diameter. We deposit this green layer, and this green layer is this single atom layer of amines. So the amine groups, it's a known chemical molecule, of course, which can bind CO2 in a reversible way. In this case, these amine groups are bound on the carbon surface, and by using atomic layer deposition, we can limit the growth of this layer to a single atom layer. And that's really important, because by limiting to a single atom layer, you keep the pore open. And the essential element here in the whole story is that after functionalization with amines, the structure is still open, so that CO2 molecules, which kind of are represented here by the red dots, can freely enter and also exit, of course, when you are regenerating the material, can freely enter and exit this region. Fast kinetics, it's all about mass transport. And mass transport means that you need to bring the CO2 molecules really fast to the molecules where they can react, in this case, the amines. In order to do that, you need to have a free path, you need to have a channel, and preferably this should be an open channel to improve the kinetics of the whole process, because typically these channels will be clogged. And if they are clogged, that means that the CO2 molecules would have to diffuse through a very thick layer of amines by means of solid state diffusion, which slows down the process tremendously, and which is the reason why in many cases it takes hours to get saturated. If the channel remains open, like in this picture, it will be a matter of minutes before all the CO2 molecules have reacted with the material, and the material is saturated, like in the picture shown here. So by limiting the amines to a single monolayer, you can improve the speed of the reaction, and you can saturate that material in a matter of minutes. And this speed is the essential part, because that means 1 kilogram, for example, of this sorbent can be reused, of course, very frequently, so can generate much more CO2 on a yearly basis. And if you translate that into the cost of machines, this leads to a much lower cost of the machine per ton of produced CO2. But it also leads to lower energy budgets, because what do you need to do to regenerate the material? It's to heat it up. And most processes, also Climeworks and Global Thermostat, they use a thermal process, a thermal swing, well, thermal and pressure swing actually. But 80% of the energy goes into heating the material. Now, if you have this material of sorbent, and if it's a slow process, you need to heat it up like for 1 hour on a certain elevated temperature, say 100 degrees, and you need to keep it at 100 degrees, and then it will slowly degas. But of course, keeping a material at 100 degrees for like an hour causes a lot of heat losses. In this case, because the regeneration will be fast as well, you simply need to give it a heat pulse. So you need to give it, you need to heat it up for a very short time to this temperature, avoiding a lot of the thermal losses that existing technologies suffer from. And that's one of the ways to improve the energy budget and lower the costs of operating the machine. In terms of costs, this technology and building a reactor with it, we think that a machine doing 100 ton per year, this could be the first generation machines could be in terms of capex cost around 100,000 euro. Lowering this to 40,000 euro, let's say, if we can mass produce these devices. And in terms of energy consumption, we think we can go as low as 1,000 kilowatt hour per ton of CO2, even lowering that further to as low as 500 kilowatt hour over time. So the energy consumption of this process can be really small. And if you translate basically these two numbers into a cost per ton of CO2, and then you see indeed that you can over time even reach numbers, let's say between 36 and 76, a bit depending on the price of the electricity, of course. But even with the first generation of machines, we could be below 200 euro per ton of CO2. These differences, let's say, in terms of kilowatt hour cost, it depends, of course, on where you apply the technology. If we think about remote locations with favorable wind conditions and solar conditions, you can actually calculate with the 1 euro cent per kilowatt hour. If you do it in more industrialized regions, you will typically have to account for roughly 9 euro cent per kilowatt hour. So of course it depends on where you apply this technology, but the price range is a much lower price range than what we've seen so far. And so the whole trick, we believe, is by improving the kinetics of the sorbent. And yeah, it's atomic layer deposition and fast kinetics. It's something that was developed for solar panels. but that we can reuse for the sake of making a sorbent that can lower the costs of direct air capture. In terms of uses, CDR effectively is capturing CO2 from the atmosphere and storing it underground or storing it in building materials, anyway, keeping it out of the atmosphere. And we talked there about negative emissions. There are, of course, other use cases than negative emissions. We can, of course, use CO2 to make synthetic fuels, to use it also in agriculture. I would say these are circular uses of CO2, which can help to reduce the emissions, or at least bring the emissions to zero. But as Toby clearly pointed out, we need, of course, to go to negative emissions, which means that we need to take it out of the atmosphere and keep it out of the atmosphere. Because by making synthetic fuels, of course, we can replace, for example, aviation fuel, fossil aviation fuel. We can replace it with synthetic aviation fuel, so circular aviation fuel, which would be good because that means that the aviation sector would become carbon neutral. But that will not be sufficient. But anyway, it's also needed, right? We cannot, let's say, clean up the atmosphere with negative emissions while people keep polluting the atmosphere with fossil CO2. We need to stop emitting fossil CO2. That can be done with synthetic fuels in a number of use cases. And at the same time, we need to go to negative emissions, which is to undo the historical emissions and stop climate change. Wrapping up, we are still a small team right now, about 15 FTE. Very much science and technology heavy, I would say, still developing this technology. So we hope to bring a first proof point by beginning of next year. But we're part of a bigger ecosystem where we have a close collaboration with knowledge institutes and universities, and also the high-tech manufacturing industry. So as I explained, I come from the world of solar panels. And we have been working a lot with these companies producing solar panels at mass scale. I believe here as well there is an opportunity to produce these machines at large scale. We will have to do that because if we want to have an impact on climate change, we will have to do this at gigaton scale. Doing this at gigaton scale means we need to produce a huge amount of these machines. It's possible. Many people ask me sometimes, like, I mean, is it even possible to produce millions of these machines a year? My answer is, it certainly is. You need to consider that the world produces 100 million cars every year. So if we can produce 100 million cars every year, I see no reason why we could not produce 100 million of these carbon capture devices. And if we get the industry to a scale that we can really produce 100 million of these devices a year, I think we can have an absolute big impact on CO2 levels worldwide. So I hope that this technology can effectively make a contribution to that. So it's a new kid on the block, I would say. Not everything has been proven, but it gives some nice perspectives. I would like to keep it here, and then we can open the floor to questions from the audience.
Hans, thank you so much for that. That was really great presentation. And appreciate all the detail on the sorbent and the process. We typically start with a few prepared questions from OpenAir, and then we will be opening it up to audience questions in a few minutes. I see a couple of really great questions have come in, so everyone please keep those coming, and we will get to as many of them as possible. Hans, you have very helpfully covered our first question, which is to talk about your personal journey to climate and carbon removal, and super interesting your solar background. And you know, we think that the cost curve that solar has come down is super applicable to DAC. And so I'm sure that that's something that you've experienced and have that belief as well. Moving on a bit, can we talk a little bit, we put this in the chat earlier, but Peter Miner from Carbon 180 wrote an article, I guess it was towards the end of last year, called DAC 2.0. And he talked about how the next generation of DAC after these sort of initial incumbents who you referenced in your presentation are going to innovate on a couple of different fronts. And number one, he talked about passive air contact And that's sort of obviously a proxy, at least partially, for energy efficiency. Number two, he talked about modularity. And then number three, he talked about moving beyond chemical sorbents. I think that you're kind of a great illustration of maybe all of those. Do you think you could just kind of recap how your process works in terms of air contact, talk about modularity and what it means to you, and then, maybe just recap at a high level, how Carbyon has taken DAC beyond chemical sorbents?
Yeah. We do an active air contact because we need to, the sorbent is so reactive that we need to supply lots of air to it. So you need to really have a very active way of exposing air to the sorbent. So we need to really blow air at reasonable speeds in order to achieve, of course, these high kinetics. So the material in itself is fast enough, but of course you also need to have a way to supply enough air. If you would just passively contact it with air, it would not work that fast. So you need, of course, to design a machine that can do this active air contact with the sorbent, which is feasible by basically blowing. And if you talk about a 100-ton machine, I think we typically talk about roughly 15 cubic meters per second that we blow through the machine in an active way with a kind of fan. So that's for sure something that needs to be engineered, but that's certainly feasible. In terms of modularity, I fully agree. We've specifically chosen not to make large systems of 1,000 ton or 10,000 ton as a single entity. I think with the solar world in mind, where you make smaller solar panels and then you can make huge solar farms with those, that's exactly the way we want to proceed. We limit the size of the machine to, say, 100 ton of CO2 per year, which is a size that you can steal from a machine point of view, that you can still manufacture in a production unit, and then you can ship it around the world, let's say, and build larger farms with it without the need for on-site integration. And I think that's a key for making or keeping the costs low. And mass manufacturing units in a controlled environment, in a production environment, and then limiting the on-site integration, very much like this is done for solar, for the solar world. So modularity is absolutely key. In terms of the chemicals, and so we use known chemicals, and we have not reinvented new chemicals, but we apply them in a completely different way. So we have applied them as a monolayer to get these kinetics, and that's using chemicals in a very, very specific, in a very new way. If indeed you use traditional chemical techniques, they involve bulk diffusion, and they're basically too slow to make this happen and to lower the cost. So it's not so much about reinventing new molecules, but applying them in a completely different way. So I concur with these messages, and we've worked on all three aspects of, yeah.
Great answer, thank you. I had the same question. Someone just put a question in the chat to the panelists. Would it be possible for you to show the timeline slide that was coming up at the end, because we were able to see what was coming next? Just then kind of give a quick overview of that, if you don't mind. If you don't mind sharing that.
No problem. I can do that last. Yeah, that's fine. I had indeed one more.
Perfect.
Yeah, there you go. Wait, maybe once. Yeah, there you go. So the timeline. So we are right now preparing a first prototype that should be ready, say, by the end of this year, beginning of next year, which will be a small-scale reactor doing roughly 1 ton of CO2 per year. And then we want to go into outdoor piloting, so making bigger reactors of the size of 100 euro per ton by the end of 2023, beginning 2024. So we would like to run these 100-ton systems. And one of the pilots that we would like to do, of course, is the X-Prize pilot, which requires us to do 1,000 ton a year. So that would be roughly 10 of those units that will be operational by beginning of 2024. And then, let's say, by the end of 2024, we hope we can indeed start to offer this on a commercial scale. So that's roughly the timeline we have for this technology.
And so if someone like Climeworks, they're kind of trying to hop at least an order of magnitude every 2 to 3 years with their plants. To get to megaton scale, you would need 10,000 100-ton machines. Like, what is a sort of your optimistic, realistic view of when Carbyon would get to megaton scale?
I think megaton scale probably from 2026, 2027 onwards. I think we plan to build the first production line that can build or that can have a capacity, so making units of 100 ton per year, so that we can produce up to say 10,000 of these units per year. So to achieve this 1 million ton scale a year. That's the idea. I think we can reach that by 2026, 2027. And so a 1 million ton sized farm, for example, would of course be composed of many of these units. In terms of footprint, if you would plan it and put it in open air, and you need, of course, some distance between these units, it would be roughly 500 by 500 meters, I think, in terms of land use for such a plant to be operational.
So 500 meters by 500 meters. Okay.
Yeah. Yeah.
That's very helpful. One thing you on your sort of beachhead market slide, OpenAir, we're big fans of using niche markets to help scale DAC. And I know that you're kind of in the Netherlands. Controlled environment agriculture is obviously a huge business, and that's a big opportunity for you. And you mentioned a couple of others. One that you didn't mention that we're really big fans of is DAC plus concrete. Have you thought about that? Is that something you like? Is that? And I'm curious too. We haven't talked to many European companies, I would say, about DAC plus concrete. Do you see that as an interesting market? Obviously, it seems like it's potentially commercially valuable. It would also have the benefit of durably storing the CO2 in a way that other utilization markets don't. Maybe a few words on DAC plus concrete.
Yeah, you're absolutely right about concrete. I should have mentioned it more explicitly because it's a very interesting use case, because of course the production of concrete today has a huge CO2 footprint, as we all know. There is a technical alternative, which is indeed making concrete on a combination of CO2 and olivine. And if you do this with CO2 from air, you actually are creating a CO2 negative building material, which has, of course, its commercial value as a building material. And it's a win-win-win situation, because, of course, you avoid the CO2 emissions from the traditional way of making concrete. And of course, you are using CO2 from air, so you are doing effectively negative emissions, doing things in that way. So concrete and CO2, I agree with you, Toby. It's a very interesting case, and we've been talking to a couple of companies about this. So the process of making concrete with CO2 is known. The challenge, of course, now is to capture the CO2 from air and turn that into a mass scale production facility. But yeah, I think there is a number of players there ready to start piloting the production of CO2 negative, so carbon negative concrete. Got it.
Cool. And I'm glad it's interesting to hear you mention olivine. I know there's some big olivine advocates in the Netherlands, so I'm sure you've been talking to them as well. One last question from OpenAir, and then again we will open it up to audience questions. And I see a bunch of really thorny questions about Solvent, so get ready. But one thing we always like to talk, particularly with direct air capture, I think it's really important to think in a practical, forward-looking, and positive way about the sort of equity and environmental justice implementations of scaling direct air capture. Both morally, just because we're creating an entire new industry, we have an opportunity to do what the fossil carbon sector did not, and not just lump a bunch of negative externalities on disadvantaged communities. But we can kind of hopefully build a new industry in a positive way. You mentioned that a 1 megaton Carbyon plant would be 500 meters by 500 meters. Can you talk a little bit more about say you're and you may be building it out in the desert or something where this might not be applicable, but insofar as you are near other communities, can you talk about what it would be like in terms of noise? Like, how would it affect local communities? What kind of nuisances or potential harms might there be? And then, as a company, how do you think about engaging with local communities and kind of talking about these things and trying to work with them, which again, I think is really important to do upfront and not sort of retroactively?
You're absolutely right. And actually, I've been working quite a while in the Netherlands with respect to solar farms and how they can be integrated into the landscape. And clearly, a country like the Netherlands is a highly densely populated area. So wherever you do solar farms, for example, you have to deal with, let's say, the people living around that and how they feel about this solar farm. And of course, there is this not in my backyard, let's say, feeling like people are okay with technology as long as it's not affecting their view or the landscape. And what we found out is indeed that if you engage with people beforehand and you allow them to participate in the project, the feeling is quite different. And participation can be in many ways. I mean, participation can be, of course, that they personally benefit from the technology, for example, in terms of the electricity which is generated by a solar farm. So in this case, by means of the CO2, which is captured from air. So people could become carbon neutral, for example, by participating in the farm. But you could also think about, and we had a discussion with the Eindhoven community. Eindhoven is the town where we are based, and we had some discussions with the local community about using this technology to make the town carbon neutral. And then we started to talk about, we can place these machines in a remote area and nobody will see it, etc., etc. And then they came with the interesting proposal. Actually, we would like to see the machines because that will actually create a much bigger commitment and engagement from the people in Eindhoven to financially participate. If, for example, over the weekend, they can take their bicycle and they cycle outside of town to the farm, for example, where you have these machines. They can go there, they can see them, they can touch them basically, and that makes it much more specific for them to see. There was even a suggestion that, as we are doing this for our children and grandchildren, maybe we can have nice designs of drawings of our children to put on these machines and all of these things. So in a way, what we're doing here, we're doing it, of course, for the people. And the people need to feel it like that and need to be involved and engaged. And I think there's many ways in which you can engage these people. I mean, for sure, it's never going to be literally in your backyard, of course, and noise levels will be very much okay. But of course, it looks like these vertical systems and a farm, let's say, of 500 by 500 meters of such systems. But if you integrate it nice and you can have trees in the middle, and there is many ways of integrating this, let's say, in a visual acceptable way, and also in a way that people can actually be proud of their local farm making their town carbon neutral. So I think there is quite a number of opportunities to turn that in a positive way. If people feel that it's their farm, and they have financed it and they benefit from it and they show the world how this technology can be used to our benefit.
It's great to hear. Thank you so much for that. Mega's going to hop on now and start sharing some of the audience questions with you. So
okay.
We're going to roll that direction, Mega.
Yeah, great. So we got a couple of questions about the lifetime in terms of number of cycles or however you measure it for the absorbent material. Do you already kind of know how long that lasts?
It's a really good question because, I mean, we've done some lifetime tests, but not very extensively yet. The material seems stable, like doing it over 100 cycles, but we need, of course, to extend this and do at least lifetime measurements of a couple of months, and we haven't done so. And indeed, there are some concerns with respect to lifetime. We know that amines can be affected. I mean, they can react with certain species in a non-reversible way, in an irreversible way. So this has to be tested in a more extensive way. And it's clear, of course, that with the fast swing technology, you will be doing a lot more cycles than with, let's say, the existing slow swing processes. But for the time being, we have no reasons to believe that lifetime could be an issue. The lifetime of the machine itself, so the mechanical parts, will be 25 years. Whether the sorbent can also live up to 25 years, it's hard to say today. It might be that we need to replace it over the lifetime of the machine, and that we need to replace it a few times, preferably not, of course, but this is subject to further testing.
Okay, got it. And then we had a few more questions about the sorbent. So maybe you addressed this a little bit, but someone asked, when comparing it to carbon engineering's approach, in that approach, you could sort of take the solvent. Oh, sorry, I guess this is about solvent rather than sorbent, but the solvent can be centrally regenerated, whereas in your system, it would be per module. So does that create any diseconomies of scale, and how do you kind of address that, if so?
And so the regeneration process is by heating up the sorbent, in this case, the solid sorbent. So there would not be an advantage of doing that in a centralized way. And you can do that modular by heating up, let's say, the smaller individual units. So there would not be an economy of scale if you use heat as a way to let's say, to regenerate the material. And in a way, if you use smaller systems, doing it by means of heat also allows to do it fast. Because if you get a very big system that you need to heat up, of course, that would take a lot of time as well. So you would actually lose the advantage of the speed, let's say, if the system would get too large. So there is, again, modularity is key. You need to keep the dimensions small, the modules small, so that also thermal processes, which inherently are kind of slower, of course, in nature. But if the system is also small enough, you can actually also there keep the timings small enough. So I understand, of course, why Carbon Engineering made the choices based on their solvent, based on potassium hydroxide. But in this case, there is no advantage of let's say, regenerating the sorbent in a centralized way.
Okay. And one of the questions actually was, how do you heat up the sorbent for desorption?
We do it in an electrical way. So the material, the activated carbon fibers, they conduct electricity. And so simply by putting a voltage across the segments, we run a current through these fibers, and these fibers heat up. So it's basically in a resistive, in the most simple way, I would say, in a resistive way. But it turns out to be a very effective way of heating the material.
Got it. Okay, makes a lot of sense. And then just thinking about the cost of the sorbent, a couple of people mentioned that tends to be one of the most expensive aspects of that kind of system. So is it, is that a main cost driver for you? Do you consider it as CapEx or OpEx? And do you have estimates around what that's going to cost in the long run?
It's true, of course, that so the cost of the sorbent, there is two parts. There is the activated carbon. And then there is the functionalization of the activated carbon with the amines, making use of this atomic layer deposition. Activated carbon is produced on mass scale, so that's not so much the concern, because this is a product that has been used since many years in huge quantities by the industry for various purposes. So the cost of the carrier, if you want, of the activated carbon is not so much a concern. The cost of functionalizing the material by means of ALD, it's a bigger concern, because ALD tends to be an expensive technology. But for the sake of solar panels and also for the sake of microelectronics, over the past 10 to 20 years, there has been a lot of investment by the machine manufacturing industry into industrializing ALD, so applying ALD such that it can be applied on industrial scale, increasing, let's say, also the speed by which these monolayers can be applied. And right now, both in the US and in Europe, there's quite some suppliers of machines that can do ALD in a very effective way. So we think the suppliers of ALD technology that we talked with, the costs of applying a monolayer of amines on these materials should not be the main costs overall. But that's thanks to the many, let's say, investments, in particular in a technology called spatial ALD. This is now going, of course, a little bit more in detail, but originally ALD is a process where you expose the material to a certain gas and then the reaction takes place and you need to pump out the gas again. With spatial ALD, they create gas curtains and the material passes through these gas curtains. And in this way, you can work at atmospheric pressures, which is not the case with the original ALD, which is working at, let's say, vacuum pressures. If you work at atmospheric pressures with these gases, of course, the reaction speed is a lot higher. And so the yield, the production yield of these ALD layers can be a lot higher. But this is not something we invented. That this is something we can benefit from. And if we couldn't benefit from that, we would never have chosen ALD as the main technology for functionalizing these materials. So I'm rather relaxed about the costs of the sorbent, but of course, we're still in the processing of upscaling the production of those sorbents with a couple of these partners in the ALD world. So the last word has not been said about it, but I don't think it's a major concern.
Okay, got it. All right, and then just thinking about MRV, are you doing that with an external partner, or do you do that internally? And the person also asked, when thinking about CDR companies doing that internally, do you see any conflict of interest around the MRV side of things?
The MRV being, sorry, can you say again?
Yeah, MRV, so like measurement reporting and verification.
Oh, yeah, sorry. No, we will. I mean, for DAC, of course, measuring the amount of CO2 that you capture is rather easy, because you have kind of an exhaust, which you can, of course, measure the amount of CO2 that goes through that. It's part of the machinery, let's say. There is, of course, a kind of meter on the machine that measures exactly how much CO2 the machine, each machine is producing. And these signals, of course, can be collected with a data collection system. So for DAC, the MRV part is not so complex, I would say. It's something that can be easily monitored from that point of view.
Yeah, makes sense. And then just one last question before I give us back to Toby. So when you think about scaling up, you're talking about making 10,000 units a year at some point. What do you think about how you'll commercialize that? Are you going to work internationally with governments or with entrepreneurs who want to start a carbon farm, and they'll be the ones, selling carbon to, let's say, like concrete companies? What's kind of the overall pathway for that?
Yeah, our role will be the one of equipment provider. So we will sell this equipment to whomever wants to use the equipment. So we will not be the one exploiting the farms or building the farms. It's a bit like in the solar world. You have the ones producing the solar panels and you have the ones producing the solar farms with these panels. Making farms around the world always take some local circumstances into account. So we will be working with entrepreneurs and with companies that are willing to buy our machines to build the farms, and our role will be mainly to supply the equipment and to maintain, of course, the equipment, but not to operationally run, let's say, the farms themselves.
Yeah. Okay. Well, that's I think all we have time for. So thank you so much, Hans. That was really great. And Toby, I'm going to hand this back to you.
Thanks, Mega. And audience, please, thank you so much for being with us and for all the great questions. And Hans, that was a great presentation, and it was really exciting to learn more about what you guys are doing. And we're, I think, inspired by the way that your product model is informed by your experience in solar. And there's a great antecedent there again for solar scaling rapidly. So wishing you that same success. But thank you for being with us. We're going to close. I'm going to try to share my screen. We're going to close with a couple of programming notes that we have upcoming. Number one, OpenAir. We've mentioned this a couple times, but we are working on in the U.S. on a national citizen lobbying push over the summer to build support for a really great federal carbon dioxide removal procurement policy called the Carbon Dioxide Removal Leadership Act. And please, there should be a link in the chat to join us. If you're interested, we have materials and everything you need to contact your local representatives to ask them to support this bill. And it's an active bill in the House, originated by Representative Paul Tonko from Albany, New York, and Scott Peters from Southern California. And in the Senate, it's sponsored by Senator Whitehouse from Rhode Island and Senator Coons from Delaware. So great bill, and we'd love to get you to help us help get it to build support. On this CDR, next week we have a really interesting and novel company from Australia that is developing a very site-specific biomass burial process called Enter Earth, and they will be joining us in the middle of their night. So we thank them for that, and we're looking forward to meeting those founders and having them tell us about what they're doing. On the 23rd, we have Carbofex, which is a biochar company from Finland, and they're doing some really interesting things, scaling biochar in like these large unitary facilities and also generating renewable energy. We're going to be announcing the rest of the sort of coming up late August and then fall program. We have Travertine, a program on ocean MRV, Lithos, which is a innovative new mineralization company, and more coming up. So please keep an eye on our Twitter, and we look forward to seeing you at future sessions. Again, next week we have Enter Earth, and the registration for that should be in the chat, and we'll leave that up for a second so you can click through to that link. And so hope to see you soon, and thank you again for being with us. Thank you, Hans, for such a great presentation. Everyone have a good rest of your